Hi, I'm Jeff, and I'm a Senior Analytic Trainer at SAS. In this video, I'm going to talk about ROC charts in SAS. Now, first of all, let me break down for you what I'm going to do in this video. The first thing we're going to have to start with is some terminology. In order to understand ROC charts and be able to interpret them, we're going to have to discuss some important terminology. Next, I'm going to take a real simple example and construct an ROC chart by hand. You heard me right. Even in this modern era of advanced computing power, I'm going to construct an ROC chart by hand. Take my word on it, this is how I survived grad school. By being able to construct a chart from scratch on our own, it's going to give us a better understanding of the information that the ROC chart is telling us and give us the better ability to interpret them. And then finally, we're going to turn to the computer. In this application, I'll be using Model Studio running on SAS Viya, and we'll look at some ROC charts in some real data. Before we jump into things, just a few more words about ROC charts. First of all, what does ROC even stand for? ROC stands for Receiver Operating Characteristic Chart. And ROC charts actually have a really interesting history. They go back to World War II when radar was first invented. But I'll have to save that history lesson for another video. What do we use ROC charts for? ROC charts are a graphical tool to assess model performance. One thing we need to know up front though is that ROC charts are only used for models built on a binary target. So in our toolbox of analytical tools, we need to keep that in the compartment for assessment on binary targets. ROC charts can be used to assess the performance of a single model. Absolutely, no problem, and we'll do this when we get to the computer. But I think it's maybe even more common to use ROC charts as a graphical tool for model comparison. I can construct multiple models at once, plot them simultaneously on the same ROC chart, and I've got a great visual tool that can easily tell me the champion model, at least based on the information I'm getting from the ROC chart. Let's go ahead and jump into a whiteboard. We'll cover some of that terminology, and let's see what we can do. All right, the terminology is going to start by filling out a 2x2 contingency table. You see I've started to draw one in the upper left-hand corner of my whiteboard. This 2x2 contingency table is often referred to as a confusion matrix. Now remember, we're assessing models built on a binary target. So notice the left-hand column of my contingency table, the observed outcome. So whether we know each case is a 1 or a 0, an event or a non-event. Notice across the top, we have the predicted outcome. Now this is a decision prediction from the model. The model is predicting each case as a 1 or a 0. Now for ROC charts, we use some special terminology here. If the model predicts a case as a 1, we call that a positive prediction. If the model predicts a case as a 0, we call that a negative prediction. Now that doesn't mean anything's gone wrong. It just means that the model has predicted a case as a 0. Now, using this confusion matrix, there's two terms that we can define when a model makes a correct decision. If the model predicts a case as a 1, and the observed outcome for that case actually was a 1, then that's a positive prediction, which is correct. In other words, a true positive prediction. And such a case would fall into the upper left-hand cell of my confusion matrix. I'll just abbreviate that as TP for true positive. There's another way that a model can make a correct decision. A model might make a negative prediction, which is correct. In other words, the model predicts 0, we go back, and for that case, the observed outcome is a 0. That's a correct or true negative prediction. Again, sticking with this 2x2 table, there's two ways that models can make wrong decisions. The model might predict a case as a 1, but the observed outcome for that case was actually a 0. The model has made a mistake. That positive prediction which was made is incorrect. That's known as a false positive prediction, and that would fall into the lower left-hand cell of this 2x2 table. And the last scenario is where the model predicts a 0, it's made a negative prediction, but the observed outcome for that case was a 1. Another error has been made, that's a false negative. Now, ROC charts really focus on the first column of that confusion matrix. The ROC chart is looking at the rate of true positives versus false positives. A little bit more terminology here. True positive rate, one of the informations plotted on the chart, is also known as sensitivity. True negative rate is also called specificity, but it's not actually specificity that's plotted on the ROC chart. It's 1 minus specificity, which is equal to 1 minus the true negative rate, which is also equal to the false positive rate. So before we jump into the example, let me start to set up how this ROC chart is going to be constructed. The ROC chart is what a mathematician would describe as a unit square. It's a square where the area under that square is 1. The vertical axis is going to be sensitivity or true positive rate. And remember, it's a rate, so that's going to range from 0 to 1. The horizontal axis is 1 minus specificity or the false positive rate. And again, it's a rate ranging from 0 to 1. That's where we get the concept of a unit square. And typically, ROC charts have a line cutting across the 45-degree angle, and that's your naive model. That's essentially the results based purely on random guessing. We're trying to do better than just randomly guessing, so we're hoping that the line for our models is above and to the left of that 45-degree line. We'll use that chart to construct the ROC for our simple example that I'm about to work out. All right, first of all, when might I use the ROC chart in a business application? Well, one great scenario is a marketing context. I want to send ads to certain customers, and of all the customers that I send ads to, I know that some are going to come in and make a purchase. That's essentially a true positive case, but I know some individuals that I send that ad to are not going to come in and make a purchase. That's essentially a false positive case. So, very widely used in an example of marketing. All right, let's jump into the example. I've got 5 customers in this very simple example, customers 1 through 5. Again, I've got my binary target, the observed column. Each case is either a 1 or a 0. And in this simple example, I've got 3 observed cases. Those might be customers that have responded to my marketing campaign, and I have 2 non-events or 2 zeros. Those are customers that historically did not respond to my marketing campaign. Now, it's also very easy to forget where the model's involved here. Don't forget, this is a graphical tool to assess model performance. Well, the model gives me the next column in my simple example, the predicted column. Those are predicted probabilities that have come from the model. Now, eventually, I'm going to have to take those probabilities and convert them to decisions. That means 1s or 0s, and I'll use the cutoff to do that, but we're not quite there yet. Once I have those probabilities from the model, to construct the ROC chart, I'm going to sort based on those predicted probabilities. So this column of sorted predicted probabilities is the cornerstone for how we're going to construct the ROC chart. Now, this is a pretty simple concept. All that this is a rank order of my cases ranked by the particular model from most important customers all the way down to least important. Now, if the model's good in that rank order of customers, hopefully a lot of observed 1s would be at the top of the list, and a lot of my observed 0s would be at the bottom of the list. That's the appropriate rank order if my model's doing a good job at it. All right, now don't forget that those predicted probabilities are associated with observed 1s or 0s, and we'll be using those to calculate true positive and false positive rates. Now, I need to be able to look at decision predictions. In other words, I need to label cases as 1s or 0s. So I need a cutoff. Now, in real data, we use about 20 cutoffs throughout the entire data, and that gives us a nice smooth curve for the ROC chart, or at least enough points that we can run through a smoother and see a curve. With only 5 observations, I got to tell you that my plot's going to look a little bit like a step function, and I had to pick my cutoffs in such a way so that I can do the calculations, but I think it's going to be okay for this example. So let's suppose my first cutoff is at 0.8. So remember, my model gives me probabilities. I rank order my cases based on those probabilities. And now everybody above my cutoff, everybody whose predicted probability is greater than 0.8, I'm going to label as a 1. These are the individuals that I would send my marketing campaign to. Let's see what the true positive and false positive rates would be if I use a cutoff of 0.8. Well, at that cutoff, I've only captured one observation. It's the observation that was predicted as 0.9. And it turns out that that case had an observed outcome of a 1. So the true positive is a rate of all of the known ones, how many were captured at that cutoff. Well, I had 3 ones to start the scenario with. I captured one of them at that depth. So the true positive rate, 1 out of 3. We like to see that thing increasing initially faster than the false positive rate. That's a sign that the model's doing good. Now, what's the false positive rate? The false positive rate says of all of the zeros, how many were captured at that cutoff? Well, at 0.8 as the cutoff, none of the zeros were captured there. So my false positive rate is 0 out of 2. That's looking good also. My model has not made any mistakes in the rank ordering at that cutoff. Well, now we go deeper into the data. We consider another cutoff. Now my cutoff is 0.7 and I play the same game. Every observation above that cutoff is going to be labeled as a 1. Those are individuals that I would market to. Let's see what we've got in the data. Well, now I've got 2 observations captured at that depth. The one predicted as 0.9 and the one predicted as 0.75. And both of them were observed 1s. So for the true positive rate at this cutoff, of all 3 of the known 1s, I've now captured 2 of them. True positive rate continues to go up. I like that. What about the false positive rate? Well, again, I have not captured any of the known zeros yet. False positive rate is still 0 over 2. So from a marketing context, what does this mean on average? If I use this model and I consider marketing to everybody whose probability is greater than 0.7, I expect to have a true positive rate of 2/3 and a false positive rate of 0. At that depth, the model's doing pretty good. Higher true positive rate, lower false positive rate. That means the model's doing a pretty good job at making those positive predictions. All right, let's go down to the next cutoff. In this case, my next cutoff is 0.5, and here's the first time that the model has made an error. At this cutoff, I'm labeling everybody above the cutoff as a 1, but one of the observations I'm labeling, the one that had a predicted outcome of 0.55, historically was known to be a 0. But given this cutoff, I'm labeling that observation as a 1. That's the definition of a false positive. We're seeing our first false positive case. So at a cutoff of 0.5, I've still only captured 2 out of my 3 known 1s, and my false positive rate goes above 0 for the first time. It has increased to 1/2. And to calculate the chart, we're going to do the cutoff calculations the entire way down the data set. Now we'll cut off at 0.3, going a little bit quicker here. Of all of the known 1s, using the cutoff of 0.3, I've captured all of them now. My true positive rate is up to 3 over 3 or 1. At that cutoff, I've still only captured 1 of my 2 known zeros. And we're going to do this calculation all the way down at the bottom so that all the data is included. And by the time I have the lowest potential cutoff I can consider, I've captured everyone. I've captured all of my known 1s at that case, and I've captured all of my known zeros. So the ROC calculations are going to start with 0, 0 for true positive and false positive, and they'll always end at 1 and 1. All right, let's take these values and let's go ahead and construct our chart. All right, the first plotted point that I didn't really even show on that table, true positive and false positive rates are both 0. The first actually plotted point has true positive of 1/3, false positive of 0. I'm plotting that point there initially. Well, the true positive axis is a rate, 0 to 1, so I'm 1/3 of the way up that axis, and the false positive rate remains 0. What's my next plotted point? True positive rate goes up to 2/3, false positive stays 0. Next plotted point, true positive rate stays 2/3, but false positive rate has increased to 1/2. Next plotted point, true positive rate went up to 1, false positive rate stayed at 1/2, and then finally, I've got 1 and 1. It's going to look like a step function. With more data, with more observations, it begins to resemble a little bit more of a curve, and we can even run those points through a smoother to get a real nice curve. One thing that we like to see here for this simple example is the true positive rate increasing quickly compared to the false positive rate. That means the model being considered here is doing a pretty good job at rank ordering the cases. Now, just a few more points before we jump to the computer. First of all, there are assessment measures that can be calculated from ROC charts. In other words, I can turn this graph into a number and use that number to assess the performance of my model. One very common assessment measure is known as the area under the curve, or AUC. By simply calculating the area under the curve, that's a statistical measure that can be used to assess model performance. Now remember, the area under the whole square is 1. The area under that 45-degree line is 0.5. So typically, area under the curve ranges from 0.5 up to 1, where the bigger it is, the better it is. One final caution before we jump to the computer. In practice, if you ever see an ROC chart whose curve goes straight up and then straight over, that might indicate that you've got a perfect model. But before you run to the boss and expect to get promoted to the office in the corner with all the nice windows, you might want to check your data. Things that look too good to be true usually are. If I see the results from an ROC chart that says my model's not making any mistakes at all, I might need to pause, take a look at the data, and I might have something going on known as leakage. Leakage is information about the target available when the model's trained, but that information is not going to be available when I deploy the model. Leakage is a bad thing to have in the data set, so that's a caution. If you ever see an indication like that, probably you've got something going wrong. All right, let's go ahead and jump into the computer and take a look at the results of some real data. All right, as I said earlier, I'm using Model Studio running on SAS Viya. Right now we're looking at the data tab in my Model Studio project. For this application, we're going to pretend that we work for a grocery store that sells organics products. We're interested in predicting whether or not customers are going to purchase an organic product in the future. We've got a single binary target by, and we're making predictions based on a series of inputs. Some of them are demographic, some of them describe prior purchase habits. All right, in Model Studio, the analysis itself is actually done in pipelines, so let's take a look at what I've done in one pipeline. All right, here's the application. I've got 3 models built, a regression model, a decision tree, and a forest. Let's take a look at the ROC chart for just one of the models individually. I'll start with the forest. The node has already been run. Let me go to the results. By the way, something really neat about Model Studio is I don't have to ask for the ROC charts to be constructed. There's no property to turn on. There's no setting I have to change. They're going to be provided automatically for me as an assessment tool. So when I'm looking at the results of the forest, across the top, I need to click the Assessment tab. And one of the assessment tools is the ROC reports found in the upper right-hand corner. And I'll maximize. Now on the right-hand side, what we're looking at here is some Model Studio's ability to help us interpret the plot. Behind the scenes, Model Studio is using some natural language processing to give us a nice interpretation of the graph. But I'll be doing that for us, so no need to take a look there. We're assessing a single model right now at this time. So why are there two lines on my ROC chart? Well, one is the forest's assessment on the training data. The other is the forest assessment on the validation data. If I'm using this tool to see how the forest is performing, I'd focus on the yellow line on validation data. All right, the vertical axis is plotting sensitivity. That's true positive rate. The horizontal axis is plotting 1 minus specificity, which equals the false positive rate. We've got our reference line across the 45-degree angle. One thing I like to see from the forest right out of the gate is I like that yellow line is starting off nearly vertical and is gaining quite steeply out of the gate. That means for some of these initial cutoffs, the true positive rate is much higher than the false positive rate. That means the forest is doing a pretty good job at rank ordering those cases. Now, a reference line has been provided here on the chart also. This is where we have the biggest difference between the sensitivity and 1 minus specificity. In other words, this is really a good cutoff to consider in this situation. We see here that the cutoff is at 0.3. Based on this model, if we rank all the cases based on the probability and we use that as our cutoff, everybody above 0.3 we're going to mark it to. At that cutoff, the true positive rate would be about 64% or 0.64, and the false positive rate would only be about 16%. Ideal cutoff to use for this particular model. All right, what if I've got multiple models built and I want to use this tool to pick the champion? Let's take a look. I'm going to close that chart and close the results. I need to run the model comparison node. And essentially, one of the things that this node is doing is taking the ROC charts from the individual models and putting them in one location. It's going to be one tool, all the models plotted there. Visually, I can look for the champion based on that information. I got my green check mark. Let's go to the results. Once again, I need to click the Assessment tab. The ROC reports is in the upper right-hand corner again. This time I need to change the focus of the chart to ROC. I'll maximize. There's a lot of lines. Well, that's because each model on every partition is provided. Let me just focus on the validation data. And there's our ROC chart for model comparison. 3 lines, 1 line for each model. The purple line, which is the line for the forest, appears to be uniformly above or on top of the other lines. Well, that means if I'm using this tool to pick the champion, and remember, ROC chart specifically is looking at your model's ability to predict a 1 correctly versus predict a 1 incorrectly. Using that information, the random forest appears to be best. That's the model that I'd pick as my champion in this scenario. So that's it for this video. Take a look down below for additional resources. In fact, leave me a comment, ask me a question if you'd like to. If you liked the video, give me a thumbs up. Don't forget to subscribe to our channel. And that's it for me. I hope you learned some things. I hope you had fun, and I'll see you later.